So for today's session we start with the hybrid model. As we saw with the signal strength map, we have an accurate system, but its setup is long. While with a propagation-based system, so a GNSS-like system, it is not accurate enough, especially compared to signal strength map, so fingerprinting, but it has a short setup. So the question is, could we combine a short setup and a good accuracy? Is it possible? One solution is to hybrid both kind of systems, so to combine fingerprinting with GNSS-like. That's the goal of a model which is called the FRBHM, freeze and reference based hybrid model, which combines a signal strength map with coordinates, signal strength measurements and directions, as well as a propagation model, so a GNSS-like model. So remember, with the freeze-based calibrated model, we thought of a question which was, with several freeze indices, how can we determine which ones to use? Well, this is the idea behind the hybrid model. Since a global homogeneity is false inside a building, so when you cross walls and other obstacles, you will change more the signal fading in the building. So it cannot be considered as homogeneous inside the whole building, but locally it is homogeneous. So for instance, inside a room, the signal will propagate approximately the same way in the whole room, because the number of obstacles is globally unchanged. So as you can see here, in the room of the access point, you have no obstacles between this access point and any location. Here you only have one wall here, then two walls here for this one, and so on. There are three versions of the FRBHM. One with a simple combination, so we search a point in the fingerprint database, then we apply the FBCM with the data on this selected point. Then we have the FRBHM, which takes into account the topology for Viterbi-like algorithm while tracking the device. Then the same algorithm, but with an infinite number of locations in the Viterbi-like algorithm, which creates new problems for the Viterbi-like algorithm. So start with the simple FRBHM. This is the operations of the algorithm. So you get one mobile device measurement with RSSI. Then you find the closest point in the fingerprint database. Let's call this point P. We use P as a calibration point for the FBCM, so data from P, which is known, so whose distances with the access points are known, is used to calibrate the FBCM with relationships between the distance and the RSSI. From this algorithm you compute the distances, and then you use multilateration to compute the mobile device location based on the distances and the access points coordinates. Now let's go to the topology in Viterbi-like algorithms. So as I said, if we track the device to improve the accuracy, we need to take into account the topology if we are indoors, since the default Viterbi-like algorithm uses Euclidean distances, which cannot be possible, or which seems not consistent with a building indoors environment. So, for instance, with Euclidean distance here between A and B, we have, well, around 1 meter, but to actually go from A to B, we have to follow this path here, which is at least 8 meters. So that's not possible. So we use a graph with points inside the rooms and the corridors and so on. We can easily get the direct neighbors, so C and B, C and D, D and E, let's say A and E, and so on. And we can extend the graph with the Bellman-Ford algorithm. And here, if we want to take any location, we use waypoints in the doors to connect a graph, and then we extend the graph to the locations that we are computing in the real time. So the first graph is the discrete topology. So it's between the reference points, which are the points in the fingerprint database, which is a discrete finite set. So it's easy to build a distance matrix between all those points. With the Bellman-Ford algorithm, you get a square matrix whose size, the dimension, is the number of points in the fingerprinting database. For the continuous topology, the problem, as I said, is that you have an infinite number of points because your algorithm can return any point which is a 3D floating point coordinates, so an infinite number of points. So you cannot build a distance matrix because it wouldn't fit in the computer memory. So you have to model the topology with convex areas such as rooms defined by their boundaries, and the waypoints between the areas defined by their coordinates and the rooms they are connected to. You build the distance matrix between the waypoints, which is easy because you have as many waypoints as you have rooms in the building. And then for each use of Viterbi-like algorithm, you extend the matrix with your set of points generated for Viterbi-like. So you have your basic graph, then you add k points in it, you find which are the waypoints connected to those points, so they are connected to points in the same rooms, and then you can find the shortest path. So let's see some results about this algorithm compared to others. So we have two kinds of measurements. Some are performed on the mobile device, the other ones on the access points. We have calibration points or fingerprints here, which are the plus crosses. Access points in the second experiment, so the one with the access points measurements, and here access points for the first experiment with the mobile device measurements. For the second experiment, we have 5 access points, so we use all of them, then only a subset of them without using less than 3 points. And we also change the density of calibration points, so at the beginning we have 1 each meter, then we remove 1 and 2, so we keep this one, this one, this one, this one, and so on. Then we keep 1 on 3, so this one, this one, this one, and so on, here, sorry. And then we keep only 1 in each room, so 1, 1, 1, and so on. we use either a mobile device moving inside the building, or mobile device at several locations but considered as static, so it's staying in its location and we see how it performs. So with a static device, we see that with the measurements on the infrastructure and on the mobile device, it's better with the infrastructure, which means that the measurements from the infrastructure are more precise and stable than those of the mobile device. And the simple FRBHM is a bit less precise than the simple fingerprint map with the closest in RSI point selected. Here it's an error, it's a copy-paste of the same one, so it changes. With 5 access points, we have an even better accuracy for both solutions, but the simple RSI map is still more precise. So while moving, we use the RSI map with a Viterbi-like algorithm without the topology, the discrete FRBHM, so with the discrete topology, and the continuous FRBHM with the continuous topology. So we see that using less points in the map decreases the accuracy, but it's not a lot, so we change from this one to this one. It's 30 centimeters, here 2, here it's 80 centimeters, and so on. And when you add access points, it's even better, so we go from 6 to 5 meters, 6 to 5, 5.4, 4.8, so using more access points improves the results. However, we see that it's less precise than the simple algorithms, so we think it's not significant because the test building is not very big, so it's hard to move in a consistent path inside the building. We walk 5 meters, we make a U-turn, go to the stairs, and so on, so it's hard to result on movement to improve mobility in such environment. So we see that the reference-based system perform better than the propagation ones, and that using the FRBHM with mobile-centric measurements, and even better with access points-centric measurements, improves the propagation-based system while requiring not as many points as the basic fingerprint-based systems.